Welcome to video 2 in our discussion of systematic reviews and meta-analyses. We are going to talk a little bit more about the statistics and some interpretation and biases that will impact us when we try to apply the results of these study designs to clinical practice. So, a systematic review, to reiterate, is the structured process for identifying and analyzing existing studies that address a specific research question. When we're analyzing systematic reviews for internal validity, unlike the other study designs that we've looked at thus far, we can't say on the surface whether systematic reviews are analytic or descriptive, prospective or retrospective, or interventional or observational. Rather, it's totally dependent on the underlying literature that the systematic review is composed of. So when you perform your literature search, depending on the criteria you use, you may have different study designs, so you need to take that into account when you're writing up your systematic review. If you have a really large randomized controlled trial, which gives you certain results, and then maybe a case control study, which gives you different results, you may trust the randomized controlled trial more because it's a higher study design and has higher internal validity. So keep that in mind. In a schematic form, a systematic review involves identifying all pertinent literature. The investigators then screen the literature for eligibility and outcomes, and then this results in a set number of studies from which you will analyze and synthesize the results. If quantitative synthesis is not feasible for various reasons, then you would just describe the outcomes qualitatively, and it would be a systematic review alone instead of a systematic review and meta-analysis. As we discussed in the first video, meta-analysis is the quantitative synthesis of data which combines information from multiple investigations identified within the systematic review that was already conducted. Again, like the systematic review, the internal validity assessment is based 100% on the underlying literature. So always look into the underlying literature because you'll come to very different conclusions. You can't simply look at meta-analysis on the surface and say, oh, I know that analysis is the highest level of research, if the meta-analysis is composed of case control studies which were improperly conducted. Then maybe your meta-analysis is not as high quality as you think it is, and maybe we shouldn't be applying these results to practice. Whereas if you had a meta-analysis which is composed of randomized controlled trials, and all of which were well conducted, and you have a new pooled estimate, maybe it's extremely beneficial for clinical practice, and that would be the highest quality of evidence. So a meta-analysis in a schematic form is very similar to the systematic review, except once we have all of our studies that meet our eligibility and outcome criteria, we can quantitatively pool them and then run an analysis to have a combined endpoint that summarizes all the existing data. The question then becomes, how are we actually combining studies? So let's look at this in a little bit more detail in a study example with nominal variables. Once we have our studies, we take patient outcome data from each individual study and then pool it in a combined analysis. So in this example, let's say that we've asked a study question and we have 5 different studies which have varying sample sizes and varying outcomes. To have a pooled relative risk, it's a little bit more complicated than just taking the average of each individual study. Rather, we weight each study based on some sort of criteria. Some meta-analyses weight studies based on the sample size. Some studies weight the studies based on the inverse of their variance, which also gives higher weight to studies with more patients. And there are also a couple other ways to weigh the studies. But the most important thing to take away is this kind of general equation. You have a relative risk, let's say for study 1, which you multiply by the specific weight of that study. Then you add that to the relative risk of study 2, which is also weighted by its particular sample size, and so on until you've summed all of your studies. The null hypothesis, again, for nominal variables is relative risk of the exposed divided by the relative risk of the unexposed. So our null hypothesis is essentially a relative risk of being equal to 1. So let's look at this in detail. We have nominal variable studies, 5 of them, all of which have varying sample sizes and varying relative risks. We then look at those studies in a slightly different light and we weight them based on their sample size or variance, and then we develop a pooled relative risk here. And again, what we're doing is we're multiplying these values, these relative risks, by a particular weight, and then we're adding them all together. In this case, our pooled relative risk was 1.22 after we multiplied each individual relative risk by its percent weight. You won't be asked to perform your own combined analysis for quiz or exams. It's just important that you know kind of how we're arriving at these conclusions. Importantly, in addition to pooling relative risk, you could also pool the confidence intervals from each individual study. So that will, in the end, lead you to a pooled confidence interval. And you can use that confidence interval along with your point estimate relative risk to assess whether that relative risk is statistically significant. This example is good in that it's simplistic, but it's bad in that if you look at the individual studies and the relative risks in the outcome column here, it kind of brings up the question, why would you perform a meta-analysis in this case? Because they're all kind of showing the same sort of finding. Although you could perform the analysis to have a greater certainty of the overall magnitude of the relative risk effect. A very similar procedure can be done for studies which use continuous variables. So continuous variables, unlike nominal variables, have a different null hypothesis. Remember, we're essentially looking at the mean of the exposed group or intervention group minus the mean of the unexposed group. So the null hypothesis is essentially that the mean difference between groups is 0. Continuous variables if we had continuous variables for our 5 different studies, we don't look at relative risk, we look at mean difference and how far away that is from 0, as opposed to if they were nominal variables and we're looking at relative risk and how far away that is from 1. So when we're pooling mean difference, it will be very similar to the relative risk example. We'll take the mean difference of study 1 times the percent weight of that same study, plus the mean difference of study 2 times the percent weight of study 2, and so on until you've summed up all of your studies. Again, we transfer our studies into a format in which we weight each of the studies by a particular factor, whether it's that sample size or the inverse of variance or what have you, and then we perform our equation up here, and we have a pooled mean difference of negative 2.672. And this time I pooled the 95% confidence interval so that pooled confidence interval is from negative 3.36 to negative 1.98. I compare that confidence interval to the null value 0, and since my confidence interval does not contain 0, then I can reject the null hypothesis and say that the pooled mean difference across these 5 studies, which is negative 2.672, is statistically significant. Meta-analyses have a couple of unique ways of presenting data to show how different studies weigh into the overall analysis. And this type of graphic here is called a forest plot. Forest plots are used to graphically depict outcomes of individual studies which show both the pooled estimates and the 95% confidence intervals. So this is an example of a forest plot for a particular blood pressure study which I just pulled off of PubMed. So each row in this forest plot represents a different study. So the first study was done by this author, Backrus et al. In 2012. It tells you the weight of the individual study. So this study is contributing about 16% of the overall weight in the meta-analysis out of these 7 studies. And then here we've got our effect size. So blood pressure medication 1 decreased blood pressure by an average of negative 5.6 compared to blood pressure medication 2. So you can see that the mean difference of negative 5.6 is also represented over here by this square. And each square represents a point estimate of that individual study. So for continuous variables, remember, we're talking about mean differences. But if this was a nominal study, this is where the relative risk would be. The size of the square is proportional to the sample size of the study. So you can see this down here in this study, the square is quite a bit larger, which means that it has a larger sample size compared to, let's say, this study here by Ernst et al., where the square is very small. So the lines that also bisect the squares, those are the 95% confidence intervals. And so you can see here, for instance, for the Backrus study, that the mean difference is negative 5.6, and that's where the square is at. And then the 95% confidence interval went all the way from negative 8.3 to negative 2.9. So not only can I tell the results of the first study, I can also tell that it's statistically significant. So for the null hypothesis for a continuous outcome, it should be 0. And you can see 0 on the graph here with this line, this vertical line. And that represents the null or the line of no difference. The Backrus et al. Study has a confidence interval which does not cross 0, right? And so that means that it is statistically significant. You can see that the next study down by Dorsch and colleagues in 2011 has a weighted mean difference of negative 1.62, which is also depicted here by the square. And the 95% confidence interval did cross 0, which means that the study showed no significant difference between groups. And there were a couple other studies here, just these like couple ones below that, that also crossed 0 and showed no significant difference between groups. However, at the bottom here, this diamond is going to represent our pooled estimate. Okay, so once we combine all these studies, we have this diamond, and the line going through the diamond, this vertical line here, is going to represent the total pooled estimate, which in our case is negative 3.26. And you can see that, right here in this row. And then we know that it's statistically significant because the edges of the diamond here, which represent the 95% confidence interval, do not cross 0. So we know that that's statistically significant. So let's look at one more example because this is sometimes confusing to students. Let's look at a nominal variable. So remember, with nominal variables, our null hypothesis is the relative risk between groups, and the difference of relative risk would be 1. So this plot of blood pressure trials looked at a nominal outcome. So do patients on prophylactic aspirin for diabetes bleed more than patients who take placebo? So presence of bleeding, which was yes or no, is a nominal variable. And in this study, there were only 3 studies here. And you can see that right over here. Were made up the meta-analysis. So again, we can see the author, study group over here on the left-hand side, and then the results of the individual studies and the point estimates here, which are the odds ratios for each individual study and how they are weighted. And so, for instance, in the first study, we have an odds ratio of 3.06. And that means our blue square over here falls at about 3.06. And then the size of the square, again, is proportional to the sample size. And you can see the confidence interval here goes from 0.98 to 9.5. And so 1 is included in that range of values, so it's not significant. And so it just barely crosses 1. The second study here which is weighted higher, has an odds ratio of 0.9. So it's, but it still straddles 1, and you can see the confidence interval is much smaller, which means that the study either had a much larger population or much more certainty of the effect. And then finally, our third study down here had an odds ratio of 8, but it also had a very wide confidence interval, and we can see that it is actually right on the edge of 1, so technically it wouldn't meet statistical significance. You can also see why these studies would be great for a meta-analysis, because they're very different in their odds ratios. So when we pool all the studies together to get this diamond down here, we see that this is our point estimate for our odds ratio, and it states that it is 2.14. And then our 95% confidence interval here is quite large. So it goes from 0.63 to 7.33. So it is crossing 1. You can see that with the diamond. So it's not statistically significant. So that's how we analyze forest plots. In addition to the results and statistical significance, like any other study, we also need to take a look at bias. There's a specific factor in meta-analyses called heterogeneity that we also need to be cognizant of. So remember that systematic reviews and meta-analyses are dependent on the existence and validity of their underlying previously published studies. So the biases in those underlying studies will also impact your meta-analysis, which again is why you really need to read those underlying studies closely. There's also publication bias, which will really impact our results. So publication bias, as we had mentioned earlier on in the semester, is when studies with positive findings are far more likely in the medical field to be published than negative studies. So positive studies are far more likely to be written up by study investigators. And if you have a negative study, you might not have the motivation to publish that. So since we're totally dependent on previously existing literature to conduct a meta-analysis, if we only have positive studies, this can lead to a very falsely skewed view of the efficacy and safety of medications. To have a really accurate pooled estimate, we need to have all available data, positive and negative, to have the best possible estimate for practice. There's also something in a meta-analysis called, like I mentioned, heterogeneity. And heterogeneity simply reflects the variation of results from studies which were included in the meta-analysis. So as we saw in these previous 2 slides, if we have a lot of different studies which have very different outcomes, it might mean that the studies simply came to different results from random error alone. But sometimes it's far more likely that the varying results stem from either different study populations of the individual studies, different study designs, or different components of the intervention, like different dosing regimens or different dosing duration or something like that. If your studies are too different, they probably should not be pooled together to give you one estimate, because you'd be averaging 2 very different things, and it would be giving you an estimate that doesn't tell you much about either one of those groups alone. We'll talk a bit more about this in one moment. For now, let's talk about funnel plots. Funnel plots are used to assess publication bias in meta-analyses. They're based on the statistical premise that there should be a natural variation around the true estimate. For these figures, we can see that the odds ratio for this nominal variable has the same vertical line at 1. That's the solid vertical lines here. Okay. This is the line of no difference. The dotted vertical lines on these figures represents the overall point estimate. So here we say that the overall point estimate is an odds ratio of, let's say, 5 in this first graph up here in the upper left-hand corner. Okay, an odds ratio of 5 should have a characteristic fan around it. Okay, and the other 2 lines here that kind of fan out at an angle are going to represent where 95% of studies should most likely fall if there is no significant heterogeneity or publication bias involved. So for this first subgroup here in this upper left-hand corner, you can see that there's a lot of variation outside of this funnel, meaning that there are studies which are very far skewed from one another and which likely reflect some form of publication bias. So to orient you further to this graph, each individual dot represents the effect size of an individual study. So they say this study had, let's say over here, an odds ratio of 10, whereas this study over here had an odds ratio of 0.2. So you can tell these are very different from one another. So on the x-axis here, we have standard error. And larger studies will tend to be towards the top of the funnel because they have less error, whereas smaller studies tend to have a lot more error and are going to be located lower at the bottom of this funnel. If they're on the x-axis here, then we have the odds ratio, like we had mentioned. So y-axis has standard error, x-axis has odds ratio. And there's a solid line of no difference at 1. And if this was a continuous variable, this solid line would be at 0 for the mean. And so then we've got our other vertical dotted line, which is our pooled estimate value. And then each individual dot is all the studies. So for what you need to know is that if a dot falls outside of the funnel plot, that is an indicator of publication bias. There's also an additional statistical test which you can run called the Eggers test. And this can tell you with a p-value whether or not you have publication bias. So as you can see in this first study up here in the upper left, the Eggers test was performed and produced a p-value of less than 0.001. And that's where, this study, we thought we had publication bias just from looking at the funnel plot, but the Eggers test is confirming that there is statistical evidence of publication bias. For each of these other studies here, these panels, you can see that the Eggers test is greater than 0.5. So there is no evidence of statistically significant publication bias. And you can see all these dots fall within the funnels on these plots. Okay. So now let's turn to heterogeneity. And so, like we said, heterogeneity is the variation in the results of outcomes within the studies of a meta-analysis. And it's calculated using a statistic called the I-squared statistic. In general, you can see this on a forest plot in which the less the confidence intervals of different studies overlap one another, the higher the heterogeneity is likely to be. Again, higher heterogeneity reflects differences in results, which are often driven by other factors such as the study design, the population, or the methods used. If there's high heterogeneity between studies, then those particular studies should not be pooled. Rather, they should be looked at separately. An I-squared as a statistic is expressed as a percent from 0 to 100%, with 100% means extremely high heterogeneity and 0% means absolutely no heterogeneity involved. I-squared is also expressed with a p-value so that we can know whether it's statistically significant. So heterogeneity is important sometimes and can actually change practice. For example, if you perform a meta-analysis and you have studies with patients with high acuity or who are very sick, and they may have different results than patients with low acuity who are not very sick. If studies which analyze these two groups individually have very different results, and so the heterogeneity is very high, you may want to analyze them separately. You may, in fact, identify that a subgroup which benefits greatly and a subgroup which doesn't benefit at all. So say that you had a medication which was extremely effective in patients who were not very sick, who had low acuity. But it was actually harmful to patients who had high acuity. If you simply average these results, you might find that you had a relative risk of, say, 2.0, which means that maybe the drug was harmful across all patients. But what you wouldn't see is that it was actually very beneficial in low acuity patients. That's why when you see high heterogeneity, you essentially do a subgroup analysis where you look at those individual populations separately and then pool those individual populations. So essentially, using the I-squared statistic is how we're going to assess heterogeneity. So if we look down here at our forest plot, at the bottom by the overall pooled estimate information, we have this I-squared value of 58%, and the p-value is 0.012, suggesting that there is statistically significant evidence of heterogeneity present, and that maybe we should not be pooling all of these studies. Rather, we could start looking at the individual studies and examining how they're different from one another and seeing if there is some way we can analyze the specific subgroups between the positive and negative studies, or looking to see if they differ in some fundamental way that's skewing our results. So that wraps up systematic review and meta-analysis. Look at the next slide to know how to study for your next quiz and exam. So, study design. You should know the difference between a meta-analysis and a systematic review and a narrative review. Remember, the narrative reviews are simply unstructured reviews which don't have to follow this systematic approach and don't necessarily involve identifying all pertinent literature. In terms of application, you need to know how to interpret the results of a forest plot if you're given nominal or continuous data. So be really wary also about confidence intervals and which type of variable you're using. Remember, the line of no difference for continuous variables is at 0. The line of no difference for nominal variables is at 1. And then bias and heterogeneity. So you want to understand publication bias and the interpretation of a funnel plot. And then you should also know how to assess for heterogeneity using the I-squared statistic.